By applying these basic principles of different sections of Earth's crust and to different landforms gives us the understanding of the distribution of the permanency of land and ocean basins. According to the theory of isostasy, the brittle zone, the Sial, which we already referred to continental landmass, floats at and also at rest on plastic mantle beneath. We have assigned the name lithosphere to that brittle zone, the term asthenosphere to the soft layer beneath the seama, where the Sial has lower density of something like 2.7 grams per cubic centimeter, and the seama has an average density of 3.5 grams per cubic centimeter. Further, erosion processes transport rock particles from mountains to adjacent plains or shallow areas where they are deposited. Once again, as I already explained, you have to see figure number 1 to get the clear view of that. As layers of sediments, they get deposited. Okay. The mountains rise a bit and adjacent plains sinks a bit. Example, our Himalayas and Gangetic Delta region. But in each interval of time, the mountain and plain will reach nearly the same level. That is the crux of isostasy. The mountains, the plastic material of asthenosphere, will flow in slowly to occupy the space vacated by the rising block of course, this newly introduced plastic material rises, it comes into a region of reduced temperature and close to become strong brittle rock, that it becomes a part of lithosphere. Again, you see figure number 1, how below the mountain land masses, the arrow indicates the pushing of that kind of material into brittle zone to form the part of the earth crust or the lithosphere. Similarly, under the sinking plane, the brittle rock mass is forced down into the region of asthenosphere. But here it is heated and becomes plastic, if forming part of the plastic zone. This excess material at depth must flow solely horizontally to escape, and it's only logical that it will move toward the region under the rising mountains. The level of the base of the lithosphere is therefore referred to the depth of compensation, as we already know it, for it is below this depth that changes the load on the earth's surface are equalized or compensated for by slow flowage of the asthenosphere. See once again the figure number 5a and 5b, you will clearly understand the process, how it happens under the asthenosphere. This figure clearly illustrates how this depth of level of compensation below land masses and ocean basins. The depth of compensation is variously estimated to be formed as shallow depth as 55 kilometers to as deep as 120 kilometers. The diagram clearly illustrates this to you. At present, earth scientists consider about 60 kilometers as working model distance. We can recollect that Pratt considered this at 100 kilometers in his hypothesis on isostasy. Let me, under this last episode, come to another sub-aspect, the aspects that prove the theory of isostasy, like gravity anomalies and isostasy. Having set up the crustal model, the next step is to compute a gravity correction based on the masses of the columns computed according to surface elevation. This isostatic correction is subtracted from the Bouguer correction, leaving a much smaller value known as the isostatic anomaly. If the crustal model is a true one and the condition of isostasy prevails, this anomaly should have zero value. In actual fact, computed isostatic anomalies range from -30 to +30 megols as a characteristics of the most surface of the continents. These anomalies take the form of small hills and depressions, reflecting place-to-place differences in rock density caused by the presence of superficial rock masses of various dimensions, compositions and structures. On the whole, however, much of the Earth's crust, both continental and oceanic, is judged to be near isostatic equilibrium. We shall find, however, that certain narrow belts associated with the mountain arcs and trenches have very large isostatic anomalies in both positive and negative directions. In these places, the Earth's crust is far from being isostatic equilibrium. Evidences of isostasy. It explains to a great extent the present distribution of land and water on Earth. When a part of the Earth becomes overloaded with large amount of sediment, as it happens even now in deltas of large rivers like Ganges, Amazon, etc., leads to geosynclines associated isostasy. Because in those areas, when you look at those great deltas, huge amount of sediments on millions of tons are accumulated per year because of erosion by rivers. Also, as happened during the past period, when part of the southern hemisphere was covered by an ice cap, the crust of the Earth sinks where isostasy is associated with the ice sheets of glaciers. The tilted shorelines of Great Lakes of North America and the upward moving of the Scandinavian peninsula are at the rate of 3 feet per century represent the isostatic recovery of the crust of the Earth from such weights. There is also another evidence that the Alaskan shoreline is tilting upward and the east coast of Africa is rising at the rate of 7 feet in about 100 years, whereas the eastern coast of North America is gradually sinking. For this, one can see a world map showing some of these zones in order to understand the specific zones under the isostatic balance. Please remember, the land masses and the other parts of the ocean basins too are all constantly under the isostatic balance, not only these regions. These crustal phenomena are linked to isostasy, which is a state of equilibrium that exists in the Earth crust. Thank you.